Today we will discuss carbon ion therapy. It is a type of heavy ion therapy in which carbon ion is used for treatment of cancer. It is a highly precise external radiotherapy which yields a better perspective for cure of radioresistant tumors. Heavy ions are those which are heavier than helium like neon, carbon. Other ion therapy includes proton therapy and fast neutron therapy. These are some radiations which are we used in the treatment of cancer, like X-ray, gamma ray, electron, pion, proton, neutron, carbon, and neon. These are the characteristics of carbon ion therapy. Bragg peak, high LET, high RBE, unique dose distribution, hypofractionation schemes, and PET imaging. First we will discuss about Bragg peak. Depth dose distribution follows rate energy loss in the medium. For a monoenergetic carbon beam, there is a slow increase in dose with depth initially sharp, increase near the end range. This sharp increase or peak in the dose deposition at the end of particle range is called Bragg peak. The Bragg peak of monoenergetic carbon beam is too narrow to cover the extent of most target volume. In order to provide wider depth coverage, the Bragg peak can be spread out by superposition of several beams of different energies. These beams are called spread out Bragg peak beams. These are generated by employing a monoenergetic beam of sufficiently high energy and range to cover the distilled end of target volume and adding beams of decreasing energy and intensity to cover the proximal portion. Linear energy transfer. It is defined as the average energy deposited per unit length of track of radiation having unit of kilo electron volt per micrometer. The energy loss per unit distance increases as the particles slow down in the medium, such that there is a peak of energy deposition at the end of track of charged particle. Therefore, these particles have higher LET than X-rays and gamma rays, that is greater than 10 kilo electron volt per micrometer. RBE, relative biological effectiveness. It is a ratio of dose of reference radiations like X-ray or gamma ray and dose of test radiation like neutrons, protons and heavy ions that produce the same biological effect. Relative biological effectiveness is directly proportional to linear energy transfer. The LET of charged particles increases as the particles slow down near the end of the range, so does their RBE. Thus, RBE of charged particles is greatest in the region of their Bragg peak. Dose fractionation. The capacity to repair sublethal radiation injury is sharply reduced with high LET radiation both for normal and cancer cells. The experiments conducted with lost neutrons and carbon ions have demonstrated that increasing dose or fraction, lower RBE of both tumor and normal tissue, but with more important decrease for normal tissue, higher therapeutic ratio for short course hypofractionation scheme. Dose distribution. Low entrance dose is called plateau and the maximum dose at depth called Bragg peak. Rapid distal fall off caused by energy loss and straggling of particles near the end of their range. A bird's eye view of HIMAC facility, a unique double synchrotron ring heavy ion accelerator system dedicated for medical use was designed and constructed. It consists of two ion sources, an RFQ radio frequency quadruple linear accelerator, an average linear accelerator, two synchrotron rings, a high energy beam transport system, and an irradiation system. A particle therapy system includes at least the following components: imaging systems for diagnosis, planning, and treatment position verification, treatment planning system, patient transport system, particle sources, accelerator and beamline, treatment beam application and monitoring system, patient position system, position verification system, and IT solutions. Treatment technique in carbon ion therapy. Radiation delivery in particle therapy is done by two methods, either scattering radiation or scanning the tumor by dividing into two slices with passive delivery and active scanning. In passive delivery, scattering fold technique or initial cyclotrons. In active scanning, there are spot scanning and Raster scanning. Passive irradiation. This is a schematic diagram of passive beam delivery and active beam scanning. An unnecessary high dose at the proximal region of target was unavoidable, and a collimator and compensation bolus should be used during passive beam delivery. On the other hand, scanning using a narrow beam is more flexible in field shaping and provides a better dose distribution at the proximal region without the collimator and compensation bolus. Ridge filter. The ridge filter device is composed of many uniform bar ridges manufactured with highly precise processing technology which are set parallel to each other on one plane. Their appropriate design of the bar ridge allows delivery of a homogeneous biological dose to the target region. Wobbler magnet. The wobbler magnet system is a pair of bending magnets which are installed so that the direction of their magnetic fields are mutually orthogonal. By applying alternating current to the two magnets which are out of phase with each other by 90 degree, the pencil beam delivered from the accelerator is rotated in a circular path. Scatterer. The annular beam is bordered by scatterer system placed downstream from the Wobbler magnet system. This is ridge filter. Passive delivery technique. Principle of the passive dose delivery system used for proton and ion beams shown is the incoming bordered beam that is modulated in depth. The variable range shifter has to shift the modulated dose to the desired depth, whereas collimator and compensator are the patient specific devices. The lines in the body represent the distal dose fall off that can be shifted in depth with range shifter. This is a sketch of a fully passive beam shaping system. The initially narrow beam is bordered by a scattering system and adapted to the target volume by various passive beam shaping devices. Adaptation of the dose field to the distal contour of the target volume is achieved by a compensator but results in unwanted normal tissue dose in the proximal part, indicated by the doubly hatched area. Active scanning technique. Spot scanning. Undisturbed focused pure beam used for scanning tumor in 3D. Target area is divided into small squared cells of the same size, filled sequentially by directing beam to each of these cells. Repositioning of beam during the process by switching on and off the beam, thus measuring the dose to each spot by fast beam monitor systems. Positioning of Bragg peak in depth is done by range shifting material inserted in front of patient. Different energy beams changed directly from the accelerator. Tumors are usually irradiated using spot scanning. The gantry targets a single spot in tumor, adjusts the energy and current of the beam, then irradiates the spot. This is monitored by computer and can deliver 10,000 spots in 5 minutes. The computer can vary the dose of each spot to take the shape of tumor into account. Instead of changing beam energy, it's often cheaper and easier to attenuate the beam using thin sheets of metal. Raster scanning, intensity controlled microbeam irradiation system, single ion delivered to individual spots with micrometer accuracy. A continuous path is selected over each isoenergy slice, digitized into a large number of voxels. When desired dose in voxel is reached, beam is shifted to next voxel without turning the beam off. Spot scanning advantage, fully flexibility since allows 3D confirmation, permits complete computer control, full beam is dumped into the patient so nothing is lost, thus reducing the need for beam intensity modification. Also, no need for activation of all components of facility. Raster scanning advantages, intensity fluctuations in beam, putting beam on and off avoided. Pencil beam moves horizontally and vertically, thus each slice corresponds to the constant energy. Space between two adjacent raster points is much smaller, 2 mm, than in spot scanning, that is 5 mm. Thank you.